All right, so continuing with chapter 6 and look at confidence intervals for the mean where our standard deviation is known. Today we're going to talk about interpreting t-distributions and how to use a t-distribution table and how to construct and interpret confidence intervals for a population mean when standard deviation is not known. So in many real-life situations, the population standard deviation is unknown. So how can we construct a confidence interval for a population mean when standard deviation is not known? Well, for a simple random sample that is drawn from a population that is normally distributed or has a sample size of 30 or more, you can use the sample standard deviation, S, as the best point estimate to estimate the population standard deviation, sigma. And so we have a formula here. All right, T alpha 2 equals T of C, which equals the mean of our sample minus the mean of population over the standard deviation of the sample divided by the square root of our n. So properties of the t-distribution. So the mean, median, mode of a t-distribution are equal to 0. The t-distribution is bell-shaped and symmetric about the mean. The total area under a t-curve is 1. The tail and the t-distribution are thicker than those in a normal, so that's the small difference there because a lot of this sounds exactly the same as a normal distribution. And the standard deviation of t-distribution varies with the sample size, but is greater than 1. So it's going to look a lot like our normal distribution. And then as we'll see, as the degrees of freedom increase, which we'll define here in a minute, we'll get a whole lot closer to that. All right, so some more properties here. It's in the family of curves, each determined by a parameter called the degrees of freedom. Degrees of freedom are a number of free choices left after a sample statistic, such as sample mean, is calculated. And then as the degrees of freedom increase, t-distribution approaches the standard normal distribution, and for 30 or more, t-distribution is close to the standard normal distribution. And so you can see here the different curves, right? We have our normal, and then there's D2, and then DF, or degrees of freedom 5, and as even that small little increase, you can see how it got much closer to our normal distribution. All right, so let's define this more. So degrees of freedom are the number of values that are free. So the number of values that are free to vary after a sample statistic has been computed. And they tell the researcher which specific curve to use when a distribution consists of a family of curves. So let's look at an example here. So suppose the number of chairs in a classroom equals the number of students. 25 chairs, 25 students. Each of the first 24 students to enter the classroom has a choice of which chair he or she will sit in. There's no freedom of choice for the 25th student who enters the classroom. There are 24 degrees of freedom. Right? And degrees of freedom because the 24 students had a choice. The 25th student sits in the last remaining, and so they did not have degrees of freedom. They did not have a choice. All right, let's look at another example here with some questions. If the mean of 5 values is 10, then 4 of the 5 values are free to vary. But once 4 values are selected, the 5th value must be a specific number. So the degrees of freedom are 5 minus 1, so 4. So again, let's highlight these main ideas here. So 5 values is 10. So once 4 of them are selected, the 5th value then has to be locked in because we have to have the mean to be 10. So our degree of freedom then comes from that. So if the mean of 5 values is 10, then what must the sum of the numbers be? If we have 5 values added together. All right, and then we divide by the number that we have. So we divide by 5. Well, what would that be? I know it needs to be 10. So then sum of those, if I multiply both sides by 5, those 5 values then have to equal 50. So if the first 4 numbers are given 2, 15, 9, and 8, what must the 5th number be? Well, substituting those in, we can then solve. Adding those together, we get 34. Subtract. And our 5th number is then 16. Now here is the nice and easy thing about this in some sense. The degrees of freedom will always be 1 less than the number of data, because the ones all the way up until that 1 less have choices. That last one then gets dictated because it has to fit that certain value for this case, or that student has to sit in the 1 remaining chair. All right, so let's look at 3 here. So find the critical values, TC, for a 95% confidence level when the sample size is 15. So let's write down what we know. We have confidence interval. CI is 95%. All right, our N equals 15. Our degrees of freedom is N minus 1. So 15 minus 1, which is 14. And then we have our alpha divided by 2 is the 0.025, because we had 95 as our confidence, and so 5% outside, and split that for our 2 tails. And so then we get, so we look here as we follow along. Right, our degrees of freedom is 14, and then we wanted 0.95, and they talk about 1 tail and 2 tail. We'll get to that distinction. And very similar to Z table, right, where we match those up. Same thing with our T table here, and that gives us 2.145. And since they're 2-tailed, 1 positive, 1 negative. All right, so using Staplet, we can also do our T distribution. So going here, you click on that. We want value corresponding, and I want degrees of freedom of 14. And we're going to go between 2, so we're the central, and we want 0.95 and calculate. And there is our negative 2.145 to 2.145. So we can use our applet as well to calculate this. And then we can then construct a confidence interval using T distribution, similar to how we did in 6.1 for our normal distribution. Both use point estimate of our sample mean and a margin of error. And so we have our formula, looks very similar to what we used previously. Right, if you look below, we have our confidence interval where the mean is known, which is this one, right? It should look familiar. And the one we now have with T distribution is when our population standard deviation is unknown. We can use a T distribution, but a lot of the setup is exactly the same. All right, so let's look over here at 4. So assumptions for finding a confidence interval for mean when standard deviation of the population is unknown. So 1 sample is a random sample, and either N is greater than or equal to 30, or population is normally distributed if less than 30. All right, so we randomly select 16 coffee shops, so not greater than 30, and measure the temperature of the coffee sold at each. The sample mean temperature is 162.0 degrees Fahrenheit with a sample standard deviation of 10 degrees Fahrenheit. Construct a 95% confidence interval for the population mean temperature of coffee sold. Assume the temperatures are approximately normally distributed. So that's there, right? And then we randomly selected. So we have our assumptions, and so we can work from there. So let's identify the pieces of information that we then have in this. All right, our N is 16. Our sample mean is 162. Our sample standard deviation is 10, so our S is 10. And then our confidence interval is 95. So our alpha over 2 is 0.05 divided by 2, or 0.025. And last, our degrees of freedom is 16 minus 1, which is 15. And so again, a little sketch of what we're looking for. We're looking for this in there, and outside this is where our 0.025 is. So we can go and use this, go to our Staplet, because we need to find our T alpha of 2. And so you can see with the degrees of freedom of 15, we have 0.95 as our central area, so we get 2.131. And then taking our equation here, we can go and substitute our known information in to find our interval. So then our sample mean, X bar, is 162 minus 2.131 times our S, our sample standard deviation, which is 10, over the square root of N, which is 16 in this case, less than or equal to our mean. And then we essentially repeat that over here, but it is going to be addition. And as we simplify that, we get 156.7, which is less than our mean, which is less than 167.3. And so then our written answer here. And so with the 95% confidence and a sample of 16, the population mean temp of the coffee sold is between 156.7 and 167.3 degrees Fahrenheit. All right, let's look at 5 here. So randomly, so that's important, right? We randomly selected. Now we have 36 cars, so we're greater than our 30, so we're good. Of the same model that were sold at a car dealership, and determine the number of days each car sat on the dealership's lot before it was sold. Sample mean is 9.75 days with a sample standard deviation of 2.39 days. Construct a 99% confidence interval for the population mean of days a car model sits on the dealer's lot. Interpret your solution with a sentence. So let's identify what we got. So N is 36. All right, we have a sample mean of 9.75, a sample standard deviation of 2.39. Our confidence interval is 99. So our alpha 2 is 0.005. And then we have degrees of freedom. 36 minus 1, which is 35. And so from there, go and try that problem on your own. So after substituting our values in and calculating, you get an interval of 8.66 to 10.84. And so then we would state, so then we would say with a 99% confidence and a sample of 36, the population mean number of days a car sits on the dealer lot is between 8.66 and 10.84 days. And then we'll graph that. All right, last one here. All right, so determining, do we do standard normal distribution or a t distribution? So is the population normally distributed? No, you can't use standard normal distribution or t distribution. Yes, is it known? Yes, that we do standard. No, t distribution. So either the start is the same, right? Either needs to be normally distributed or our sample size is greater than 30. If it's no, we can't do either. And then you just look, hey, is our population standard deviation known? Yes, we have normal. No, we use t. So as we look at here, we're not doing the confidence interval. All right, let's read through and then see our question. So you randomly select 25 newly constructed homes. The sample mean construction is 181,000 and the population standard deviation is 28,000. Assuming the construction costs are normally distributed, should you use the standard normal distribution, the t distribution, or neither to construct a 95% confidence interval for the population mean construction? So let's go through our checkoff. So we are randomly selected, but we are less than 30, so we're at 25. But they tell us, assuming they're normally distributed. So then when we go up here, is it normally distributed? Yes, so we're going to go here. Next is the population standard deviation known? Let's see what they give us. And they do tell us it is yes there, which means we are going to use the standard normal distribution. You can use the standard normal distribution because the population standard deviation is known and normally distributed.